Well, welcome to another video. So I'm going to present two videos here. This first one we've got here is the way I like to write these limit proofs, and it emphasizes how we can use inequalities to make our life better. So we want to compute the limit of this sequence given by 2n plus 3 over 3n plus 2. We can look at the sort of the leading coefficients here, and we see that the limit, as we expect from calculus, should just be 2/3. So we expect that the limit should be 2 over 3, and we want to write a proof. So the first step is always to identify what L equals, and I like to write L equals 2/3 on my paper. So what I would then do is I like to always write a template. And so the basic template for writing a limit proof, and this is something you could print out or memorize, but I would just write it on your exam or on your homework. They're always going to start by taking any epsilon greater than 0. So we write let epsilon be greater than 0. Then by the Archimedean principle, we're going to claim that there exists an integer capital N in the natural numbers, such that that natural number n is greater than something. And we haven't filled that in yet because we either need to do some scratch work to see how big of a number we need, or as you'll see in this video, we're going to get that by writing the rest of the proof first. And so by the definition of the limit, we have to show that no matter what epsilon we choose, we can find some capital N, so that if we have little n bigger than capital N, then the distance between a sub n and the limit, that's this absolute value here, that has to be less than epsilon. Right? So I've left some space in the middle. As you'll see, we'll need a lot of space to do our computations, but this is the basic setup of any proof. And I just want to remind you that it's convenient for the reader, because the reader can basically look at the definition of the limit, see that you've got epsilon in place, you've got the existence of capital N, you've got little n greater than capital N, and then you've got this final conclusion that the distance between all points in the sequence after that point, capital N, will be close to that limit. So let's just go ahead. And so what I've done here is I've simplified a little bit. I've not changed anything up top, but I've filled in a sub n minus L. I've just put the formula down for the sequence and then subtracted off the limit. And I've done some algebra, and once I simplify everything, I get 5 over 3 times 3n plus 2 in the denominator. And the nice thing about this problem is that the absolute value just goes away. So the absolute value of this fraction is just 5 over 3 times 3n plus 2. So for the next step, what we want to do is we want to compare this. We want to say that this is hopefully smaller than something. And the reason we're going to do that is because we'll be able to simplify it. And I want to now do something that's not going to work in general, but I want to write down something that's valid. For instance, this fraction is definitely smaller than or equal to 5/3. Right? And the reason is that the denominator on the left is way bigger than 3. It's 3 times some bigger number. So this fraction is definitely less than or equal to 5/3. But remember, our goal is to make this fraction smaller than epsilon. Now, if epsilon were 10 or even a number like 3, then this would work. 5/3 would be smaller than 10. It would be smaller than 3. But if epsilon is small, like maybe epsilon is 0.02, then it's not going to be true that 5/3 is smaller than epsilon. So I've written down here that we're stuck, and that's okay. It just means we have to go back one step. And so if we go back one step, we can say, well, I don't want to say this is smaller than 5/3. It probably makes sense to keep a little n in there. So what I'm going to do is I'm going to say, well, that's smaller than 5 over 3n plus 2, because I've made the denominator smaller. That's going to be less than or equal to 5 over 3n. And finally, that's going to be smaller than 5 over n. Right? So you should pause the video here and make sure you understand why this inequality and this inequality and this inequality are all true. because being familiar with those and being able to do this on your own is a great step. So now we're almost done. So now we just want to notice that we want to, our Archimedean principle is going to give us some property on capital N. And so far everything's been about lowercase n. But what's our connection? Well, our connection is that n is at least as big as capital N. And so in terms of fractions, that will mean that whatever 5 over little n is, it will be less than or equal to 5 over capital N. Again, you should pause this video and really think about why this is true. But now our proof is almost done, because now we get to do this final inequality and say, ta-da, it's less than epsilon. Now, why is that true? Well, we can ask, when is this last inequality true? It's certainly going to depend on what epsilon is, right? If epsilon is 10, then actually any natural number we plug in will make this true. But if epsilon is like, 1, then this wouldn't be true if we plugged in small numbers like n equals 1 or 2, right? So when is this inequality going to be true? Well, if you solve this inequality for n, you'll see it's precisely true when n is at least 5 over epsilon. So what I'm going to do is, now that I've got that, I'm going to fill in that answer up here in the blank. So here it comes. So now we've got our complete proof. Let's read it one more time. We're going to take an arbitrary epsilon greater than 0. By the Archimedean principle, we're going to take some natural number that's bigger than 5 over epsilon. Then we're going to take any natural number n greater than that capital N, and we're going to go through all of these steps. All of these are equal. Now we get into our inequalities. Now we transition from lowercase n to capital N. Again, these are the most important inequalities here. You should really make sure you understand what's going on with those. If there's one you don't know, please send me an email. And then finally, the toughest inequality is maybe this one here. Why is 5 over n less than epsilon? Well, that's precisely how we've chosen it. Okay. So there's an accompanying video to go along with this one that shows maybe a more traditional way to try and solve these problems using what we might call scratch work. I'll present that one as well for this example, and I'll let you decide which one works better for you. I like this one a lot better just because it reduces the amount of algebra that I have to work out. But I'll show you the other one as well. Great, thanks.